Hello and welcome back to another episode of Math with Stone. Today we're going to be doing some AICE physics from March 2021, paper 2-2, questions 4 and 5. So, first one is state the principle of superposition, and it is worth 2 points. You got to come up with two things that would work. Now, superposition can work in a few different ways. It could be a wave that is coming this way, and then another wave that is coming that way, the opposite direction. When they combine and they hit each other, they ending up making it bigger, okay? So knowing that that is the idea of superposition, then we need to come up with two things that would actually be what AICE would think, and what better way to do that than to just tell you. It's when two or more waves, I like the or more, meet at a point, that's what we had right here, and the resultant displacement is the sum of the individual displacements, which is fancy wording for saying that the amplitude here and the amplitude there would combine to make a bigger amplitude, thus creating a superposition. Okay? Now, this idea could work both constructively and destructively. I showed constructive, which is what superposition is, but destructive would be the opposite, and that would be when you have one wave up and another wave down, and they cancel each other out when they meet. Okay? So, here's our main problem. We have a transmitter is producing microwaves that travel in air towards a metal plate in figure 4.1 as shown. The microwaves have a length of 0.04 meters, and a stationary wave, which I would call a standing wave, is formed between the transmitter and the plate. Explain the function of the metal plate. This is only a singular point, so it's not going to be too complicated. So what would happen is if we send these microwaves down, and knowing that we just talked about superposition, some of these microwaves are going to reflect back and then create a stationary wave in a superposition, and some of them will be constructive and others will be destructive, and the purpose of the metal plate would be just to reflect what is happening. It's going to reflect it back. Okay, so all it's doing is reflecting it back, and one of the ways that this could happen is if we had a full wave here, we would have a full wave again, and then it would reflect back, creating maybe a standing wave position that looks something like this, where here and here and here, we would have destructive interference. These would be considered destructive. And then at the amplitudes, it would be considered constructive. Okay? But the purpose of the metal plate is just to reflect that microwave. All right? So that is all that is doing. Now, same diagram, same thing. I've just reprinted it essentially. The microwave has a wavelength of that, of the 0.04 meters. A stationary wave is formed. Calculate the frequency in gigahertz. Gigahertz is 10 to the 9th power of microwaves. So we have to think here a little bit, and we have to understand that velocity is equal to frequency times wavelength. And we have to be careful about what is our velocity. If it's sound, it's normally 330, but if it's any electromagnetic wave, and microwaves are electromagnetic waves, then it would be a speed of c, which is 3 times 10 to the 8th meters per second. So I'm going to plug that in for velocity. We would have 3 times 10 to the 8th would equal frequency. We're looking for frequency times wavelength, and the wavelength is 0.04. So if we divide 3 times 10 to the 8th by that 0.04, you would get an answer of a lot. Oh my gosh, that looks awful on my calculator. It is 7.5 with a whole bunch of zeros, and it turns out all those zeros, 7.5 with a lot of zeros, ends up equaling 7.5 gigahertz. So quite a few hertz, and that's actually worth 3 points. And if I show you the mark scheme, they give you these points for a few different things. See how here you get 1 point, 2 point, 3 point. If in this case, if you get the right answer, that would give you all 3 points. But in some cases, you could maybe mess up, and if you just write the formula correct, you get 1 point. And then if you can plug it in, you get another point. And then if you can solve, you get your third point. But in some cases, you get all points by just having your answer. Not all the cases, and you will not know which one is which. So I recommend always writing down the formula, substituting it in, and then writing your answer, which I did. I wrote down my formula, I substituted it in, and then I got my answer. Okay, so I would have gotten all 3 points. I didn't do it as fancy as I should have maybe, but I would still get there. Okay, now we're getting the interesting things. A microwave receiver is initially placed at position X. Here's position X. All right, where it detects an intensity minimum. The receiver is then slowly moved away from X and directly towards the plate. So I'm going to go back to my original picture here. So here we would have constructive interference. Here at every dot where they're overlapping like that, that would be destructive interference. And they want to know what is the minimum distance. I believe, what does it say? It says the receiver is then slowly moved away from X directly towards the plate. Determine the shortest distance from X the receiver could be when it detects another intensity minimum. All right, so we have X here, and it was doing this, and we had these guys right here. So we essentially want to know, when does it reach this other minimum right there? Well, I just drew an entire wavelength, right? That entire wavelength, I went and only went half of that wavelength. So I need to figure out what is just half of a wavelength. And we were already told that a full wavelength is 0.04 meters. So if a full wavelength or a full lambda is 0.04, if we do that and divide by 2, I get a distance, and then we want it in meters, and this was provided to us originally as a wavelength in meters, as 0.02, and we would be done. All right, let's see what the mark scheme says there. It was just a 1-pointer. I didn't write the points for this one. It was just 1 point, and we would have gotten it. So get your answer, you're done. No partial credit there. 2 is a more interesting question. It says, determine the number of intensity maxima that are detected by the receiver as it moves from point X to a position 9.1 centimeters away from X. All right, so I'm going to try and show both diagrams here at the same time. No, I'm just going to do this one. So right here we're at X. And if we move, and this distance from here to here is 0.04, well, I can't, like technically we guessed what one of these positions would be. I can't move 9 centimeters. I would run into the metal plate. This is just one of the potential standing wave positions. You could have a whole lot more. For instance, on my other diagram, we could have one that does quite a few of these before reaching the metal plate. And I'll just pretend that it reaches the metal plate there. And we could have each of these where we have the humps being maximas, okay? So all of those could be represented as maximas. And in this case, I have 1, 2, 3, and 4 wavelengths, and each wavelength is 0.04, which ends up equaling 4 times 0.04, ends up equaling 0.16 meters, which is good news because we needed to be at least able to move 9.6 centimeters, and 0.016, that is 16 centimeters. So we're good. All right, so we need to figure out how many of these, if we go 9.1 centimeters, would we have? So we would have, our first maximum would occur when we were at our quarter wavelength, but I don't want to really think about that. I'm just going to label my first one, that's 0.04. Then we would have our next one at 0.08, and then our third one at 0.12. 0.12, we would have already gone too far. So let's count up our maximums up to that point. We'd have 1, 2, 3, 4, and then are we going to get the fifth before we reach 9 centimeters? Well, this spot right here where it's destructive would be at 0.10. That means we would have our fifth constructive occur before that spot. So we have 1, 2, 3, 4, 5, and we wanted to figure out how many intensity maximas we would have as it moves 9.1 centimeters away. Well, by the time we get to 10, that's too far, but we had 5 maximas before that, and that would be the number 5 maximas. All right, that is the end of that question, and it is the end of paper 2, paper 2-2, question 4. I'm going to do another video to do question 5. All right, until next time, stay positive, my friends. I will see y'all later. Bye.